Hello and welcome to this video about making ESC hardware from almost scratch, compatible with VESC firmware. As a first disclaimer, don't treat this as a tutorial of any kind. I'm not qualified to teach people about motor control, so this is just my personal experience gained while working on this project. Second disclaimer, my controller is named VESC and it's based on the VESC, which is a registered trademark owned by Benjamin Vedder. So whenever I refer to VESC in this video, I mean electronic speed controller hardware that is compatible with the VESC ecosystem. I will also get a bit technical, so I will assume you know the basics of electronics like current, voltage, resistor, MOSFET, etc. Let's begin. This whole journey was sparked by my dissatisfaction of existing ESC controllers. Despite the plethora of options available, none of them seem capable of handling the high voltage for applications using 40S batteries. And even if there were some, either they were impossible to buy or used gigantic IGBT modules. There seems to be a gap in market of controllers beyond 150 volt but below 400 volt, which I was hoping to fill. I did not start this project because of commercial reasons, it was purely just to learn and experiment. But who knows, if there's sufficient demand, I may spin some board for production. Given my background in electronics, albeit more digital than analog, I decided to start developing custom hardware compatible with VESC. When I researched a couple of years ago, nothing could really hold a candle to VESC in terms of features and flexibility. This is because VSC isn't a specific device, it's an entire ecosystem. It includes many parts such as controllers, motors, accessories and tools that work together extremely well. It's simply a league on its own compared to the other options. I knew that developing a working PCB would take quite some time. Even though VESC schematic is public, I had access to some third-party ones produced by the other enthusiasts. I knew it wouldn't be a simple copy-paste. The very first step was deciding on parameters my controller should have. From the start, I knew I wanted to fully support 40S batteries, which means handling voltages around 168 volts. The closest standard breakpoint to this is 200 volts, so whenever I picked components connected to the main voltage bus, they had to be rated for 200 volts or above. That's where I hit first hurdle. Take a look at how many MOSFETs support 150 volt with decent current capabilities. Now compare that to how many can withstand 200 volts. There are about 5 times more options available when you use lower voltage. So you may be asking yourself a question. Why not just settle for 150 volts? The answer is simple. It's easier to deliver power to the motor with higher voltage. And lower voltage means bigger cables, more heat, less efficiency, and a lower maximum speed. Of course, this wasn't going to be a controller designed for EVs. My focus was mostly on electric unicycles and perhaps e-bikes, e-motorcycles, and other medium-sized personal electric vehicles. So the size was the next most important thing. After all, it has to comfortably fit between the rider legs. I checked a couple of ESC models and they all seem to be between 150 to 300 mm wide. Therefore, I wanted my controller PCB to have a maximum width of 100 mm, which also gives me a better price from PCB manufacturers. Length wasn't as crucial, but if I could find an enclosure roughly matching my expectations, it would save me some money. And what do you know, those cheap extruded aluminum boxes from Hammond offered many choices, so I picked 2 sizes and started designing PCBs around them. Because I just started this motor control journey, I decided to split the controller into 4 PCBs, which later settled on 3. Main logic board, power stage, and a power supply. Initially, I also had socketable MOSFET drivers, but I quickly realized that would create too much hassle. Anyways, splitting the design allowed me to iterate separately on the different parts without redoing the entire controller. This idea turned out to be great, but I'll talk more about this later on. Now that I had my design constraint ironed out, I began working on the schematics, starting with the microcontroller. If you analyze the heart of the VSC, you realize it's almost just a bare MCU with a few voltage dividers, RC filters, connectors, and LEDs. I fully admit I copied the pinout from another VSC, because it was way easier than trying to do it from scratch, especially considering STM32 chips do not have internal MOOCs capable of remapping every function of the microcontroller to any pin. I just didn't want to mess with any ADC or PWM pins. However, I chose a bigger MCU, namely STM32F407, to give myself a bit of flexibility for remapping simple GPIO and peripheral pins. 407 series is basically the same as 405, so we can use VESC firmware without any issues. I have also added standard stuff like decoupling capacitors, 8 MHz crystal, boot reset buttons, and 2 diodes. The power section is also pretty standard. It uses DC-DC converter based on the TPS4530 to supply entire board with 5 volts and the LDO regulator for 3.3 volts. There is also a high precision voltage reference and a jumper to switch the voltage for the MOSFET drivers. After all, if I wanted to use a classic silicon MOSFET, I need the drivers to work with around 12 volts, while a gallium nitride FETs needs 5 volts. The accelerometer and gyroscope use the LSM6DS3 chip, connected to the main MCU via the I2C bus. This setup is as simple as it gets with just 2 pull-up resistors and 2 decoupling capacitors. Now the connector page is where things get a little interesting. Because I have used MCU with more pins, I decided to connect as much as I could, starting with the auxiliary power connector. This board requires external power, so there are 2 redundant pins labeled as 15 volts, though they are actually for 12 volt input, along with the 2 ground pins. There is also an input voltage sensor using a simple voltage divider, and a couple of pins that are currently unused but can be driven by the microcontroller. Next, there are 2 SPI connectors. First one shares the functionality with 2 external ADC pins, which can be used, for example, for throttle control. There's also a JTAG connector for programming the microcontroller, a Hall sensor connector with thermistor input intended for motor sensors. Additionally, there are 3 extra UART connectors, CAN bus connector with TGA10050 chip, a USB connector for PCB connection, and last but not least, servo connector. This connector accepts a PWM signal with a frequency around 50 Hz and a variable pulse width from 1 to 2 milliseconds, similar to signals from the cheapo blue servo testers. Filters page consists of both switchable and permanent RC low-pass filters for signal conditioning. Those filters are used for sensing phase voltage and current, as well as selecting motor Hall sensor voltage. There's also a filter for the motor thermistor and a battery voltage. Getting this part right was crucial because a noisy signal can cause the ESC to misbehave. There's also hardware protection, which I won't go into detail about since it was generously provided by a community member. I'm not sure how much I can share and I don't want to claim it as my own. I can only say it's a fast hardware comparator designed to react when a certain amperage threshold is reached, theoretically disabling transistor to protect the system. I did also cram VESC Express into this board, fully copied from the original schematic to enable Bluetooth connectivity. And the last part of the logic board, connected to the largest 30-pin header, is the FET drivers. This specific model, hard to pronounce but let me try, 2EDF7275KXUMA1, was also a recommendation. What's unique about it is that it can work with both traditional silicon MOSFETs as well as GaN FETs, because it has undervolt lockout at around 4 volts. Despite its tiny size, it's advertised to handle 4 amp source and 8 amp sink current. I decided not to use GaN specific drivers because this was just an experiment. Gallium nitride transistor could have some issues that I may not be able to overcome, so I wanted the flexibility to revert to more classic solutions if needed. It was a bit of a gamble, but so far I do not see any real downsides. I just had to make sure to pick driver that will work with 5 or 12 volt, since GaN require 5 volts on the gate. Don't be fooled. Reaching this point wasn't easy. The logic board went through 3 major revisions, but overall I didn't encounter any significant problems with it. Most issues were related to interboard connectors. Long story short, I wasn't satisfied how the logic board connected to the power stage board. And for now I settled on using one large connector on top of the PCB, along with 4 M3 standoffs. Needless to say, I worked on the logic board PCB simultaneously with the power stage PCB to make sure all the connectors are in the same spot. Easiest way to do that is to design PCB in absolute positions to each other. For example, logic board PCB is a rectangle that starts on a point 106x57 and ends on a point 206x125. Now we can use that to draw the same rectangle on the power stage PCB so that we know where it will be positioned. Using this technique, we can also position all the holes and interboard connectors by specifying a known and absolute coordinates. Power stage is also a relatively simple design with just a couple twists. I will spare you the details of the amount of iterations I did and just say that it wasn't hard either. Just a bunch of iterations to incrementally fix some of the small mistakes or issues that popped up along the way. Mostly related to, yet again, interboard connectors. Thinking about cooling also took some time to figure out. Single phase consists of 3 pairs of transistors in half-bridge configuration, thermistor, lots of capacitors, and a Hall current sensor. Now let's talk about the twist I was talking about earlier. First one is making use of 50 amps Hall current sensor parallel with shunt to boost its capabilities to 250 amps. Yes, I know I will use resolution and precision, but overall there are no high current sensors in small packages, and the big ones like ACS 758 are extremely hard and cumbersome to position on a PCB. Second twist is ferrite beads on the transistor gates. Believe it or not, they pretty much eliminated all the ringing I was seeing on the oscilloscope. This is a solution used in one of the commercial products, suggested to me by another community member. Now the waveforms look really clean. Along the way, I made prototypes for traditional silicon MOSFETs in D2PAC package, also known as TO263, because they are extremely common and could be used to make a budget version of my controller. Although I never went as far with them as with the APC2304, which is just unmatched value for its price, at least on paper. I tried different footprints as well, but never really produced any PCBs for them. During my work on ESC, I learned a couple of important things. First, current measurement is crucial for ESC operation. The cleaner it is, the better the controller behaves. If there is any issue with the current measurements, there is no point in proceeding further. The same goes for phase voltage measurement, but here we just use a simple voltage divider plus an RC filter. I ended up choosing GaNFETs, specifically APC2304, which proved to be a great value for several reasons combined. It offered competitive price, handled 200 volts with high power, had low RDS on, a high CSS to CRSS ratio, and came in a compact size. After some initial testing, they turned out to be even better than I thought. In addition to the previous reasons, they proved to be insanely fast switching, resulting in lower switching losses. Their ability to be cooled from the top due to exposed die was another advantage. In case of a critical failure, they would simply pop out of their socket, leaving the circuit in an open loop. This is unlike traditional MOSFETs, which often end up welded to the PCB, creating a short circuit and potentially destroying the entire board. Why is this advantage, you may ask? Like Adam Savage used to say, failure is always an option. Naturally, I don't want to design a controller that shorts itself out, but knowing that in case of a short, the GaNFET will pop gracefully gives me a bit of additional comfort. APC2304 was not easy to implement due to its very unusual footprint. However, after reading some recommendations from manufacturer regarding the layout, I eventually figured it out. Initially, I was able to achieve 10 nanoseconds turnout time with around 30% overshoot while testing at 150 volts and 100 amp pulses. After some more tweaking, I settled on 20 to 30 nanoseconds turnout time with no overshoot at all, meaning they should be theoretically able to handle 180 volts. Now let's talk about the biggest, most painful part of the controller yet, the power supply. I needed to step down 30 to 200 volts down to 12 volts, and surprise, there was no ready chip nor power brick that would support such a wide range of inputs. I mean, there is one, namely LT8316, which works, but I am very adverse to depending on a single chip. And while I did try it, it was simply too big, considering the transformer was like 25 x 25 millimeters, which is to be expected with flyback topology. Experimenting and designing a power supply for my use case easily took 80 to 90% of overall time spent on the entire ESC. I could make a whole series of videos about this topic, but I figured it would be very boring, so here's the condensed version. I've tested around 6 different power supply designs, but each had problems. Some were too large, namely flyback topology. Some had hard to find components. Others were unstable, and a few had output ripple that was just too high, or a mix of these issues. Eventually I found a solution in a manual old-school DC-DC converter, which relies on a TL494 PWM controller as its central component, paired with a MOSFET driver. This choice offered reliability and simplicity I needed for the project. While the converter showed promise initially, it had its own set of issues that needed some intense brainstorming to overcome. While dealing with these issues, I reached out for help on electric forums, discords, and even asked friends who knew more about analog circuits. I was even willing to pay someone to help me figure it out. But even with all that, it was still trial and error process. Along the way, I ended up burning at least 3 MOSFETs, 1 drivers, and 4 of those controllers. Because I also have a regular job to juggle, this whole process stretched out over a course of about 6 months before I finally got it all sorted out. It's still not perfect, but now it can handle voltages up to 190 volt like it's nothing. And it's capable of outputting up to 3 amperes, which is pretty decent, but completely unnecessary. I don't even remember how many iterations it took, but it was really driving me crazy. I don't really want to talk about the list of the issues in this video as it's getting too long anyways. If you guys want to see more in-depth video about the power supply, let me know in the comments down below. Now that I had all the electronic pieces sorted out, the last thing was to ensure it was mechanically sound. There are 2 important parts, cooling and assembly. Because I chose an off-the-shelf enclosure, assembly was more or less set in stone from the beginning. The PCB can slide into grooves, making it a friction fit. If a more permanent connection is required, silicone or glue can be used to keep them in place. I have 2 plastic side panels where I could drill holes and route cables. Phase outputs to the motor can be routed either to the side or through the drilled holes in the front. Top connectors can be angled for front connections or kept straight if you want to route the cables through the side panels. Power supply and power stage PCBs are held together with 6 screws and a copper bus bars. Those bus bars allow for more current flow without heating the PCB too much. The logic board latches onto the power stage board with a 30-pin connector, and it's also supported by 4 standoffs. On the bottom of the power stage, there's a piece of aluminum that acts as a heat spreader. It's bolted to the PCB to maintain contact with the GaN transistors with either thermal pads or thermal putty. This block is also designed to transfer heat to entire enclosure, which should be sufficient for normal usage. However, since the enclosure is made from raw aluminum, you can always mount additional heat sinks or even water cooling if needed. Now, let me get straight to the point. This design is called DevKit for a reason. It wasn't designed for mass production, rather for ease of disassembly and tinkering. Everything can be done by hand with just the basic tools without the need for CNC. And that's really it. I managed to get it working pretty decently on the workbench. I did not test it yet with the proper battery and under the load, but I did perform a bunch of tests making sure the double pulse test can reach at least 100 amps. I also checked for basics like confirming current sensors are performing well, motor can be detected, voltages and temperatures are decent and so on. This is the end of this video, not the end of this project. I hope you enjoyed it. Consider subscribing if you don't want to miss my M motorcycle conversion with this controller.